How can you tell if two groups are what we call isomorphic, which means that they are really the same, except for perhaps a renaming of the elements? So maybe this group is exactly this one, except that here we call the elements 0 through 7 modulo 8. These are pairs of classes modulo 4 and modulo 2, but there is some way of renaming elements so that the two groups are essentially the same group. Well, in this case, they are not. They are really different, but how can you tell that they are different? Another way to tell groups apart is their order, but this is a group of order 8. There are 8 elements, and this is also a group of order 8. There are 4 possibilities here, 2 here, so there's also 8 elements in this group, so they are the same in that respect. Another way to tell groups apart is whether they are cyclic or not cyclic. Here, Z modulo 8 is cyclic because the number 1, for example, generates all of Z modulo 8 under addition, but however, Z modulo 4 cross Z modulo 2, this direct product, is non-cyclic because, well, if you take any element, AB, and multiply it by 4, I will get 4A, 4B, and that will be 0 modulo 4 and 0 modulo 2, and therefore, any element in here has order at most 4. And in fact, every element has order 1, 2, or 4, and this is not a cyclic group. So that's cyclic, this is non-cyclic, so they are different groups. They cannot be isomorphic. What about these two groups? The dihedral group D4, the rigid motions of a square, versus the quaternions, Hamilton's quaternions. They're both groups of order 8. They have 8 elements, and they're both non-abelian. So can they be the same group? Is there an isomorphism between them? Is there some relabeling of elements such that the operations, the binary operations on these groups, is just exactly the same thing? And the fact is no. These are actually two different groups of order 8. How do we prove that? Something we can do is compare the number of elements of each order in each group. And if those numbers do not coincide, then they cannot be the same group. In D4, the identity has order 1, the rotation by 90 degrees has order 4, the rotation by 180 has order 2, and then 4, and S, RS, all of those 4 elements have order 2 because they are reflections on the square. So notice that all in all, we have 5 elements of order 2 in D4. But in Q8, there's only one element of order 2, and all these other elements have order 4, except identity. So there's only one element of order 2, while in D4, there are 5 elements of order 2. So they cannot be the same group, because otherwise there would be the same number of elements of order 2.